Good afternoon. My name is Niklas Balk, and I'll be presenting a summary of my MSTC capstone research project titled Modeling Fluid Flow Around a Vehicle. I worked under the mentorship of Dr. Christoph Brehm at the College of Engineering at the University of Kentucky. To give an outline of my presentation, first, I'll be going over the background and introduce my topic a little better. After that, I'll be going over my experimental questions and hypotheses. Next, I'll cover my methodology. After that, I'll go over my data and conclusions. Next, I'll cover the future research that I hope to carry out with this. After that, I'll show my references, and then I'll acknowledge those who have helped me along the way. And after that, I'll turn to the audience for questions. Now, CFD, or Computational Fluid Dynamics, is software that is capable of calculating precise airflow. So it's not just one specific software, but it refers to any software that can do this with precision. So it more often than not will require a supercomputer to do because of the complexity of these tasks. And even with a supercomputer, these simulations can take days or even weeks to finish. Now, lastly, CFD will require a mesh to do. For more terminology, the angle of attack is the angle between an object's path and the airflow. So for example, if you have an airplane taking off 5 degrees above the ground, that would be a 5-degree angle of attack with a horizontal airflow. The Reynolds number is the ratio of inertial to viscous forces on an object. So the inertial forces would be forces that are a result of the object's momentum, whereas viscous forces are forces that keep air on an object and they counteract each other. Now, the important takeaway of a Reynolds number is that an increase in a Reynolds number increases the turbulence that acts on the object in most cases. Turbulence is chaos or just unpredictability in airflow. And true turbulence means there is really no pattern in an airflow. Laminar is the opposite of turbulent, and it refers to airflow that is nice, smooth, and easy to predict. The Mach number is the ratio of an object's speed to the speed of sound. So for example, an object traveling at Mach 5 would be traveling 5 times the speed of sound. And hypersonic flow, just like supersonic flow, is a certain speed. So for example, a hypersonic vehicle would typically be traveling at Mach 5 or greater, whereas supersonic would be Mach 1 or greater. Now, there are 2 parts to my project, and that's why I have 2 hypotheses. So first, I was looking at the effective angle of attack on the air density of a specific vehicle. And I looked at the air density around the vehicle as a whole. And I also wanted to look at the turbulence as a whole. I hypothesized that increasing the angle of attack decreases the average air density around the vehicle. And the other part of my project was to look at the effective Reynolds number on the tail length of an airflow. And this was done at a low speed, whereas the first part was done at a hypersonic speed. And for my second part, I hypothesized that an increase in Reynolds number increases the tail length as well. Now, I'll get more into what tail length is when I get to the images, but for now, just keep in mind that tail length is the area of an object that is, or the area of an airflow that is going the opposite direction. Now, for my methodology, all you need is a powerful computer, hopefully a supercomputer, and a couple programs. So first, you need a mesh generation software. I used star CCM. And then you import that mesh file into the CFD program of your choice. I used Dr. Brehm's own that he had created by himself. And then you run the simulation with the appropriate constraints like the Mach number and the Reynolds number. Lastly, you just generate the images and see what you can find from them. Now, here's my data. So on the left is my Reynolds number test, and on the right is the angle of attack test. And you can see that I tested Reynolds numbers of 20, 40, 60, and then 100 just to see what it would be like up there. And for angles of attack, I chose 0, 2, and 6. Now, if you look at, sorry, I skipped a slide there. If you look at the pictures of the angle of attack tests, The orange and red and yellow refer to high or average air densities, whereas blue and green are lower. So you can see for the images on the left and the right, where the left would be a side view and the right would be a cut view. This was at 6 degrees, and you can see that there's a very low air density on the bottom and a high air density on the top. For the Reynolds number tests, the left would be at 100 and the right would be at a Reynolds number of 20. And you can see the differences in airflow between the two. The right is more laminar and the left is more turbulent. Now, to conclude my AOA tests, the hypothesis was fully supported. So even though the highest value of the air density didn't decrease in any significant margin, the low air density decreased significantly, which decreased the average air density. Now, the reason for this, if we go back to the pictures, is because the air density, the airflow is coming from the top. And so the air on there's a lot of air on the top, and that's why the density is very high. But then that leaves out air on the bottom. So it creates almost a vacuum or a pocket of air that just is much lower density, because it's getting essentially ignored by the airflow. And so this has bad implications in real life, because it really implies just turbulence, because if there's a lot of air density on the top and then low on the bottom, or vice versa, then that will mean that air will start to travel around the cone, which is not something you want. And this can cause turbulence for the aircraft. The big takeaway of these tests is that angle of attack increases turbulence in a significant way. Now, to conclude my RE tests, you can see that the hypothesis was supported up to a Reynolds number of 60, where my Reynolds number increased, the subtail and tail lengths also increased. So the tail lengths would be the dark and light blue sections of the airflow. So this is because the key you can see is the velocity in the right. That's the direction of the airflow. And so blue and dark blue are negative values. And so if it's blue or dark blue, it's going in the opposite direction of the airflow, which is not something you typically want. And so as you increase the Reynolds number up to 60, this length increases. But at 100, you can see that it's tiny. And the reason for this is because 100 is kind of an outlier. Although a Reynolds number of 100 in this case is actually not turbulent, because there is a pattern to it that you can see, it's clearly much different and much more turbulent than the other cases, which are obviously limited. And so my conclusions from this is that in laminar cases, the tail length does increase with Reynolds number, but after that, it's fairly unpredictable, and that turbulence really has nothing to do with tail length. So in the future, I would really hope to explore more cases with higher turbulence, as well as cases in between Reynolds number of 60 and 100 to see where this breaks down. And what I'm doing right now is actually using Python to automate my results. So this is on two fronts. One is that I'm trying to use Python to automate this like simulation on the mesh in the first place at different Reynolds numbers. And I'm also trying to get Python to find out exactly where the tail ends in the actual data file. Because as it stands right now, we extrapolate our data from the images, because the actual data files are really difficult to read because it's massive arrays of numbers. So I'm hoping to use Python to be able to pinpoint where the tail actually ends. And lastly, I would like to apply these Reynolds number results to nasal airflow itself, because that was the original intent. If you look, you can see that the cylinder cross-section was actually meant to be a blockage in the nasal cavity. And that's why this was done at low speeds, because you're not breathing at Mach 6. So I'm hoping to apply these results to nasal airflow to one day be used to help surgeons or just other people in the medical field deal with people with breathing problems. Now, here are my references. And lastly, I would like to acknowledge a lot of the people and organizations whom, without them, my research would not be where it is. So first, I would like to greatly thank Dr. Christoph Blin. He is an associate professor in the Department of Mechanical Engineering, and he is my mentor. And without him, I would never have started this in the first place. And of course, the University of Kentucky and the College of Engineering have supported me as well for allowing this research to happen. The Kentucky Young Researchers Program has supported me greatly as well, and the MSTC program. The facilitator, Mrs. Karen Young, I would like to thank her for her support. And lastly, I would like to thank family and friends for their support during this. If you have any questions, please email me at balknicholas@gmail.com. Thank you.